Welcome to Physics 2426, University Physics 2. And we're going to pick up in Chapter 21, which introduces the idea of electric charge. And the idea of electric charge goes all the way back to ancient Greeks. The Greeks would have a piece of amber and they would rub it. And when they rubbed it, they noticed that it then could exert a force on another piece of amber that was likewise rubbed. If we were in class, I'd actually show a demo of this in which I take a piece of plastic and I'd rub the piece of plastic with some wool, and I'd rub another piece of plastic with some wool, and one of these would be hanging from a thread. When I put it close to each other, it repelled. Okay. Now another thing that you can do is you could actually take a just piece of metal that you've not rubbed, and then put the piece of plastic you've rubbed near it, and it's going to attract. And so we'll talk later about why such a thing would happen. But this is the beginning of study of electricity. And so in fact, the word that we use, electricity, to describe this, or electric charge, comes from electron, which is Greek for amber, because they noticed this with amber or dried tree sap. So when we do this, we discover very quickly that the electric charge exerts a force, and this was very difficult to really measure until you started, being able to measure electric charges, or get enough electric charges to really measure and quantify. But interestingly enough, Benjamin Franklin actually studied electricity, and we'll talk a little bit more about how he did that later. But Ben Franklin studied electricity, and what he noticed was you'd have one object here and another object, object 1 and object 2, that attract each other, but object 1 and object 3 would repel each other. But if you put object 2 and object 3 next to each other, then what he discovered was that if object 1 and object 3 repelled each other, if object 1 and object 2 attracted each other, what do you think would happen with object 2 and 3? And so he would say, well, in this case, what he discovered was that they attracted each other. And so he started working this out, and eventually decided that there's two types of electric charge. And so he arbitrarily calls one type positive and the other type negative. So this was totally arbitrary. It's like, you can't tell by looking at it if it's positive or negative. And so he just called one type positive and the other type negative. So that became our basis of electric charge. Now, I frankly think he got it backwards, because it's 50-50. You pick up a charge, say that's positive or negative, and I think he picked an awkward convention for us, because we got electric charge, and we have electric current. Electric current is the flow of electric charge, and we're all familiar with the example, a battery, like an automobile battery, has a positive and a negative terminal, and if you connect the two together, then current flows. And the way we define the current is the amount of electricity flowing from positive to negative. Well, as it turns out, what really happens is electrons, which are negative, are coming out of the negative terminal, and they're going into the positive terminal. So while electric current is defined to be the flow of positive charge, electricity, as you normally know it, is the flow of electrons, which are negative. So that means if the current is going this way, so that's the direction of electric flow, what's really happening is electrons are going that way, making this side more negative, and so forth. And so that's what's really happening. So that's why I say he kind of got this backwards. So in discussing electricity or electric charge, this actually brings up the idea of flowing electric charge. And so, as I said, we talk about electric charge flowing. And so, an object or a material that electric charge flows easily in, we call a conductor. An object that electric charge does not flow in is an insulator. Now, what we're going to discover is that this is not really an accurate description of materials. You know, metals conduct electricity, glass insulates, but there's not really a separate between the two, because what really happens is no conductor conducts perfectly. Some conduct better than others. No insulator insulates perfectly. Some can insulate better than others. In fact, any insulator does allow a small amount of electricity to trickle through anyway. You can actually verify that if you want to. Typically, if you got an automobile that's running, if you put one hand on the fender and then reach in and grab a spark plug wire, you discover that even though it's insulated, it's not perfectly insulated, and generally you never do that again because it's not very comfortable. But so I would recommend don't actually do that. But no insulator is absolutely perfect, though some of them are better than others. Now, there are a group of materials between the two that sometimes conduct and they sometimes don't conduct, and so that would be a semiconductor. And so in this class, we are primarily going to concern ourselves with conductors and insulators. And that's going to be our main focus for this semester. Semiconductors, we'll mention them a little bit as we get later on into the semester, but they're not going to be a main focus for us. We're gonna treat this semester as idealized conductors and insulators for the most part, just to understand how electricity works, and how electric charges work, electromagnetism, and then in later classes you introduce the idea of the continuity between these two and semiconductors, and how they work. So, in studying electric charges, one of the things that we realize is that you can measure the amount of electric charge. And so we'll talk about how you do that in a second, but you can measure the amount of electric charge. And so what happened was, in the earliest days of studying electricity, they were just measuring charges, and they defined a unit of electric charge to be a Coulomb. So this is the SI unit of electric charge. Symbol of Coulomb is C. Now the thing is, a Coulomb is actually a fairly large amount of charge, and so in this class we're going to frequently deal with microcoulombs. We even have picocoulombs or nanocoulombs. So we normally talk about very small charges, so you need to be familiar with the prefixes on the SI system that go down to very small. Micro is 10 to the minus 6, and pico is 10 to the minus 12. Charles Augustus Coulomb, for whom the unit was named, was one of the ones that was measuring the properties of forces. And we would have a charge, and the symbol we use for electric charge is Q, because we use C for other things. So we have Q1 and we have Q2 over here. And so he realized that there's a way of measuring the force between the two. Well, obviously, since charges either attract or repel, and what Ben Franklin discovered was like charges repel each other and unlike charges attract each other. So it doesn't really matter if we increase Q1, that's going to increase the force between the two, because it's going to either attract or repel the other charge by more. So it's going to be proportional to Q1. Well, likewise, Newton's third law says with symmetry here, it doesn't really matter which one you call 1 and 2. So if you change the other one, it's going to do the same thing. So this is proportionate to Q1. It's also proportionate to Q2. Okay. Well, if you move the charge to the other side, it also is repelled or attracted the same way there. In fact, anywhere you put in the vicinity of this, if you're the same distance away from it, it feels the same. So everywhere the surface of a sphere of that same distance, it's the same. So whatever effect the charge is having, it's distributing that effect over the surface of a sphere. So if you're closer, in other words, on a smaller sphere, you're distributing over less of an area, so the force is going to be stronger. If you're farther away, you're distributing over a bigger area, so the force is going to be weaker. So that means it's inversely proportionate to the area of a sphere. Well, the area of a sphere is 4 pi r squared. So this is inversely proportionate to r squared. Now, there's got to be a proportionality in here. That proportionality, K sub E, is what we call the electrostatic constant. And so this is Coulombs Law. The electrostatic constant, K sub E, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And so that's Coulomb's law. There's the electrostatic constant that's in there. The constant is determined by the strength of the electromagnetic force. It's determined by the arbitrary choice of units that we have, and it's also determined by the geometry of space. So the 4 pi and everything else goes in there. So there we have it. Now, interesting thing. Later on in the semester, we are going to end up discovering that in equations, we routinely get 1 over 4 pi k sub e over and over again. So that is given its own symbol, epsilon naught. Epsilon naught is the permittivity of free space, and so epsilon naught is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. And again, you get that by just taking 1 over 4 pi k sub e. And so that's just, again, it's just a constant. It's just that it's easier to write epsilon naught than it is 1 over 4 pi k sub e. So later in the semester, we see it that way. Your book, as soon as they define Coulomb's law, they immediately start writing it as 1 over 4 pi epsilon naught Q1 Q2 over r squared. That's the same as what I just wrote, K sub E, Q1 Q2 over r squared. Both of those are just different expressions for Coulomb's law. And you may use whichever one you wish. I like to use whichever one gives me the fewest things to write down. Because the fewer things you write down, the fewer things you plug into the calculator to get the answer, the simpler it comes to be. In vector form, this is going to be K sub E, Q1, Q2 over r squared, r hat. Okay, where r hat is a unit vector pointed away from the wherever your origin is. You put your origin either at Q1 or Q2, so it points away from there. So that means if both of these are the same sign, it's pointing away, so it's repelling. If one's positive and one's negative, you get a negative vector, which means pointing back towards one another, and so that's an attractive force. And so that's the vector format of this. So I'll pause that for right now, and then next we'll start introducing the idea of a couple example problems. I'll work a couple example problems for you.